Now the question that comes to our mind, you know what? What is the question that comes to our mind? To predict word 3, third word, how many ANNs have you stacked? Answer this question. To predict the third word, that means you predict the third item in the sequence. Let's say word 1, word 2, word 3. To predict the third item in the sequence, how many ANNs have you stacked one after the other? In this example, how many ANNs have we built? We stacked 2 ANNs. To predict the fourth word, let's say you want to predict the fourth word, word 4, by taking word 1, word 2, word 3 in the sequence, and you want to predict the fourth word. How many ANNs we may have to stack one after the other? First, we have to build AN word 1 to word 2. Then we have to take the partial output from there and build it using when we are building word 2 to word 3, which we have done. Now fourth one, third ANN model, this will be ANN 1, this will be ANN 2, which you are already taking some partial output. You have to build ANN 3, some partial output. The same process need to be repeated. That means if you are predicting the 10th word, if you are predicting the 10th word, how many ANNs you have to manually stack? If you are predicting the 10th word, automatically 10 minus 1, 9 ANNs you have to stack. Now that is a very tedious process. Don't you think it is tedious process? Even stacking 2 ANNs itself is becoming very tedious for us. Stacking these many ANNs, stacking n minus 1 ANN models when you want to predict the nth item will be too much tedious. Is there an automated way? Is there any automated way of automatically doing this? Is there a way directly all these ANNs are built, all these n minus ANN, n minus 1 ANNs are built, automatically stacked together. Their hidden layer outputs are considered and given as input to the next ANN, and hidden layer output considered given as input. Is there an automated way of doing it? Yes, there is an automated way. These are known as RNNs. RNNs are nothing but reoccurring recurrent neural network. These are the programmed sequential model building techniques. They will automatically build this. You know what? Whatever we have done until now manually, everything that we have done until now manually is already automated. We don't need to go through this much of pain. Automatically it is done. All that we need to do is we have to use RNN. That's it. You don't need to do anything else. You just need to tell what is your input data, how many time steps. That's it. RNN will automatically build these identical ANN models. RNN will automatically stack it. Then you might ask me, why did we do all this? We did this whole exercise to understand how RNN works internally. How RNNs are working internally, that is what we understood. But in reality, we don't need to follow this much of process. Not required. RNNs are very similar to the manual sequential ANNs model that we have just built in the previous lab. RNNs are built for sequential input data because they work this way, sequential. RNNs will automatically, important point, automatically build multiple ANNs in a sequence. RNN also takes care of sequential dependency. That means this word is coming after this word is coming after this one. There is a sequential order that is important. RNN will automatically take care of it. RNNs are also known as ANNs with memory. Why they are called as ANNs with memory? We are carrying some information from the previous ANN, some information from the previous ANNs. RNN will build multiple ANN models sequentially, connect them automatically. So this is the architecture of RNN. The sequential ANN models that I told you, that is nothing but RNN only. RNN, recurrent. You understand the term recurrent, reoccurring, recurrent neural network. So this is ANN1, ANN2, ANN3, ANN4. This is the RNN architecture. When you are predicting this, you will use this input as well as some partial input from previous time step. You will use this one, you will use this one. Automatically this uses this one. That means when you are predicting this, you are taking input from here, here, and here. RNNs are layered ANNs over time. Time step 0, time step 1, time step 2, time step 3, like that. So whatever we have done until now need not be done, need not be created, need not be done manually. All that you need to do is give the data, word 1, word 2 data need to be given. That's it. You just tell RNN, hey, predict word 3 for me. RNN will ask you, just tell me how many hidden nodes are required. We just need to configure that. That's it. If we say, okay, 10 or 20 or 30 hidden nodes are required, that's it. In every ANN, identical ANNs, which means in every ANN, it will put 30 hidden nodes. If you want to predict the third word, then automatically 2 ANNs will be built automatically by RNN. So we just need to use one function, that's it. Simple function. Single RNN function, if you use, automatically it will do it. RNNs are layered ANNs over time. Then what will RNN do? RNN will find these weights from input to hidden. RNN will find these weights from hidden to output. These weights from hidden to hidden. Usually we call them weights, weights, weights only. But here in RNN, there's a different terminology. These weights from input to hidden, they are known as set of weights U. These weights from hidden to output, those are known as set of weights V. These weights that are from hidden to hidden, these are weights that are known as set of W. Weights from input to hidden, hidden to output, all of them are weights only, but shown with different terminology. Weights going from input to hidden, use. Weights going from that set, that is going from hidden to output, set V. Weights going from hidden to hidden, set W. This is the RNN architecture. Have you understood the RNN architecture, all of you? Why it is shown like this? This is ANN1, this is ANN2, and there is this connection. Have you understood this architecture, all of you? Will you be able to follow this architecture next time when you see this? Do you understand what is this connection? This ANN, anyway, we understand, but the connection between them, why it has to be connected, that and all, you got the intuition behind RNN? You know what? This is known as unrolled version of RNN. This is unrolled version. There is a rolled version. Imagine this is a sheet of paper. Okay. Imagine this sheet of paper. Okay. If it is like this and you start from this side, you keep on rolling it and it will come like one, cone kind of thing, not cone, cylinder kind of thing, isn't it? When you roll it, that is the most widely displayed RNN architecture, which is known as rolled one. It is shown like this. This is the unrolled version. When you roll it, imagine this paper, if you roll it, it will just look like one stick kind of thing. Input to hidden, hidden to output, hidden to hidden. It will be shown like this. Now have you understood this connection hidden to hidden? First time it will be kind of confusing. What do you mean by hidden to hidden? Now have you understood what is hidden to hidden? Previous time step hidden to current time step hidden. Current time step hidden is connected to previous time step hidden. Hidden to hidden. So next time when you see this, you should follow this. You should understand this is nothing but RNN. RNNs are usually shown in this manner. Input, hidden, output. However, hidden is connected to hidden. How many ever time steps are there? If you unroll it, I think unrolled version is easy to follow. Maybe you can consider the unrolled version. Whenever you see this rolled version, you unroll it, then it will be easy to understand. Or you can put any other manner as well. Input, hidden, output. Current input will be next layers or next ANNs. Current hidden will be input for the next ANN model. That is also another way of showing it. That is the intuition behind RNN. Have you got the intuition? Okay. Now the way the weights are found, the usual back propagation only. If you take single ANN, forget about RNN. If you take single ANN, you have input layer, you have hidden layer, you have output layer. And what is that song that we sing? What is that? What is the first step to find these weights? If I want to find these weights, what do? We follow back propagation algorithm. So we start with random weights followed by feed forward. Yes, take the data, do the feed forward, followed by, so once you reach the output, then what will happen after feed forward? We do the error calculation, back propagation, and then followed by weight correction. That is a single ANN, back propagation. Whereas here, since there are multiple ANNs, so the feed forward will happen from here to here. Again, it'll go until the output, actual eventual output. So feed forward in the time step 1, time step 2, time step 3, time step 4, time step 5, time step 6. Time step means, let's say if you are predicting the third word, two time steps are there, time 1, time 2. Time 1 is word 1 to 2, time 2 is word 2 to 3, like that. Time step 1, 2, and so on across the time, through the time, until the last one. So feed forward will go until here. Then what is the next step? Error calculation, back propagation. Error calculation, back propagation will keep on happening until the beginning, followed by weight correction. So the theory and all that remains the same. The only thing is this will be back propagation through time. Time step 1, 2, 3, 4, and all this. This will happen not just in one layer, it will happen across all the ANNs. This is known as back propagation through time. So back propagation through time is used by RNN. Automatically, it will give us these weights at the end of it. So eventually, what I am trying to say here is, all of you please focus, whatever we have done until now, taking word 1 as input, word 2 as input, taking this sequence as input, predicting word 3 as output, we don't need to do it manually. Automatically, there is a model that is available. That model is recurrent neural network. All that you need to give is just the data. Do the one hot encoding. Yes, you have to do the one hot encoding. Do the one hot encoding. Give me the data. Then RNN will take care of it. It will give you as effective results as you have manually built. Let us see how to build RNN model. So check this out, all of you. Building the RNN model to solve the previous problem. Preparing the data. X3 is word 1 and word 2 in one shot. No need of ANN1, ANN2. One shot you give word 1, word 2. Of course, we have to do the categorical, two categorical. One hot encoding need to be done. We will do it. Okay. Y3 is word 3. So take X3, do the one hot encoding. Check this out. Since you have two columns and each one of them will be one hot encoded, you will have rows 5, 3, 5, 1 rows. Okay. And there will be two columns. Each one will be 139 one hot encoded values. Do you understand this X3? It is a tensor. It is a multi-dimensional tensor. Rows, columns, and each column is one hot encoded, isn't it? 139, 139. Yes or no? Do you agree with that point? Yeah, it's like that. We keep it like a tensor. We don't keep 139 here and then beside it 139, 139 plus 139, 278. Actually, it will be maintained as a tensor, three-dimensional tensor itself. Since we are working with TensorFlow, we don't need to really fix it into a two-dimensional data every time, isn't it? We just have these many rows, these many columns, and this is the depth of each of the column. Got it? Yeah, we can maintain it this way also. And Y3 shape will be what? What will be Y3 shape? This is straightforward. Number of rows will be 5351. Number of columns will be how many? 139 columns. Okay, that's it. Then this is the example of X3, one of the column. So maybe this is column 1. This is column 2, one hot encoded 139. Then give it to the RNN model. Look at this. This is the model building code. This is the model building code. If you understand this, only these 4-5 lines are required. That's it. The most important piece of code until now, whatever we have discussed, is this one. And you must understand this piece. Let me explain this in depth. Model 3 equal to sequential. That is anyway, we write it for every model in Keras. Model 3 dot add. Simple RNN is the function. Okay. Simple RNN. 30. Can somebody make a guess what this 30 could have been? What is this 30? So 30 hidden nodes in every ANN. So 30 hidden nodes in every ANN. These are all identical ANN models stacked together. How many ANNs RNN is going to build, by the way, for this scenario? How many ANNs it is going to build internally? 2 ANNs. So both the ANNs will have 30 hidden nodes. Input shape. Input shape, we are giving number of time steps So this is number of time steps, which is 2. You remember what is x3 shape? X3 shape is 5351, comma 2, comma 139. Until now, we have the habit of giving input shape only number of input variables. That's it. However, since it is RNN, it is expecting us to give number of time steps, which is shape 1 is 2. We will give it here. And shape 2, which is 139 hidden nodes are there. Got it? Have you understood this, all of you? 30 hidden nodes in each of the ANN. And then input shape 2, comma 139. Have you understood the input shape here? We are mentioning this as the input shape. Okay. If we would have been predicting the fourth word, taking word 1, word 2, word 3, what would be the input? Here we would have given 3 time steps, and then shape would have been 139 or whatever is the shape of the data. Then finally the output layer and the output softmax activation. Okay. So let us go back to the code file. Let us build an RNN model. This is the data prep. In the data prep, directly take word 1 and word 2. Look at the shape of this 5351, comma 2, comma 139. Have you understood the shape of this X, all of you? 5351 rows, 2 columns, each is one hot encoded as 139. Since we are working with TensorFlow, we don't really need to put everything in a data frame format. We can maintain this as a multi-dimensional array or the tensor. Okay. This is the Y3 shape. Y3 shape is straightforward. So timestamps, number of time steps are 2. One hot encoded variables are 139. Check this out. 30 hidden nodes, shape, and that's it. You have to give only this bit. This is the only piece of configuration that is required. Rest everything is taken care of. That means the whole code, that 100 or 200 lines of code that we have written previously, that was just for our understanding sake. That's why I told you, even if you do not follow that code, it's okay. Not a big deal, because we will be in future using RNN, this technique, to build the model. Obviously, you will build the model, save the model, or you can already, if you have already built this model, you can take someone else's model, you can load it. Okay, here is my model that I have built. You can load this model as well, compile the model, execute another few more epochs, then get the predictions. Go ahead, get the predictions for this approach, RNN model approach. Yeah, go ahead, all of you. What are the predictions made by RNN? If you take love the, input is love the, output is way. So this particular warning, it is showing as deprecated model.predict classes. Maybe somewhere we are using model.predict classes in between. Maybe that will be removed later on. So we may have to update it with the new function, which I'll try to do it later. Allow it when love to see. Again, these predictions totally depend on what is your data. Hate the idea. That is the RNN model building and the idea behind sequential data and sequential models to solve the sequential data problem. Any questions on this? RNNs seem to be a very good idea until it hits its roadblock. What is a roadblock in RNN? The biggest issue with RNN is when the sequence is really long. When the sequence is really long, during the backpropagation, there is one particular issue. Do you remember it? Let us suppose if you are predicting word 3, that is fine, word 4, fine. Let's say if you are predicting word 30, you are predicting word 30, and there is some information that is there in word 30. The prediction here depends on this value. Let us suppose this has an impact on the word 30. Word 1 really decides what is word 30. But somewhere the impact of this word is not going away. The problem is practically when you see practically something over here, let's say you find the gradient here, you keep on calculating the gradient value, partial derivative, you keep on coming here. By the time you come here, something happens. What is that issue called? Even that was an issue with deep neural networks. The issue name is the problem of vanishing gradients. Perfect. Some of you guessed it already. That's correct. The problem of vanishing gradient. So RNN seems to be working perfectly for smaller sequences. Smaller sequences, RNN is working perfectly. Maybe when you try it practically, maybe when the sequence is 10 or less, when the sequence of items is 10 or less, then RNN is working. But when you go beyond 10, you know what? When you go beyond 10, RNN is failing because internally the problem of vanishing gradient is kicking in. Usually in deep neural networks, when you have problem of vanishing gradients, you resolve that problem using ReLU activation. But here, even ReLU activation also not working, or it is not helping us to solve this problem, because RNNs inherently will be losing some info from here, some info. Obviously, when you are reaching word 30, you cannot expect the information to be carried from word 1, word 2, or until this point, whatever we have seen, we cannot expect that to be carried forward. Maybe there is some limitation that will definitely be there in RNNs. For example, let me give you an example. Let us suppose this is the sentence: her heart was heavy because it was open, so things filled in it, so things rushed out, etc., etc. If it is starting with her, and this will be her. If you're starting with my heart was heavy, this will be me. This will be his, then it will be him. Or if you start with I'm living in Bangalore, you wrote a lot of lines. You wrote like 20, 30, 40, 50 words. Finally, you say that I reached this station. The station name is. Now, the station name, before that, there was no hint. Somewhere in the beginning, you mentioned Bangalore, but after that, you never used Bangalore. Now, the station name is Bangalore Central or something. That depends on Bangalore that you have given. Like the way her depends on here. There was no hint in between. If this is the case, something over here has long-term dependency. The word that is deciding this has long-term dependency, then RNN fails. If you are giving me 4 or 5 words, predicting the next one, based on these 4 or 5 words or 10 words, RNN works. But for long sequences, RNN fails. In real world applications, a lot of people have already observed it. A lot of experts, they have suggested that this back propagation through time have difficulties learning the long-term dependencies. In theory, it should work. In theory, no doubt about it. It should work. It should learn long sequences in theory, but in practice, you know what? It doesn't work. It doesn't work. A lot of people have seen this problem already. It is limited to looking back only few time steps. Usually some people say that 10 time steps it works perfectly. But RNN fails when it comes to long-term dependencies. Then as a solution, there have been some more modifications, some more complications added to RNN that gives us LSTM. RNN works for short-term memory. RNN has short-term memory. Short-term memory means the short-term dependencies, they'll take care of it. When it comes to long-term memory, they fail. RNNs do not have long-term memory. RNNs have only short-term memory. Short-term memory means immediate few words they'll remember, and the prediction will happen on these immediate ones. But long-term memory, they fail. So we will add long-term memory component to the short-term memory, which is RNN. So RNN is short-term memory plus long-term memory component. Both of them put together becomes LSTM. Usually it is known as LSTM only. Nobody says long short-term memory, but the complete detailed version of it is long short-term memory. It contains both long-term memory, short-term memory. Using a lot of theory, we finally get this LSTM, long short-term memory. Okay. We will take a short break and then we will discuss this LSTM.